Going back a few slides to revise some of the things that we talked about last week. But we're carrying on the discussion about sandboxing and application-oriented access controls. So we are looking at ways that we can restrict what programs can do on a computer to restrict the kind of damage that can happen, even if you've got malicious code running. So one of the problems in security is where we basically have malicious code on a computer. So we've got some malware or there's some software vulnerability where a malicious person manages to get some code on your computer. And if we've sandboxed that code, it limits what it's able to do. So even if that program is trying to do something malicious, it can't get at anything outside the sandbox, or it can't access things that it's not allowed to based on a number of rules. So last week we talked about isolation-based rules. So we talked about things like chroot and using virtual machines and all those sorts of approaches to confining a program to just see, like a limited namespace, just see a bunch of files that it's allowed to interact with, and everything else is outside of the scope of that program and it just can't do it. Today we're talking about rule-based sandboxes and rule-based access controls where we have a program with a finely grained set of rules about what that program is allowed to do. So again, it's restricting what a program is allowed to do. It restricts the kind of damage that can happen because it can't access, for example, the camera on your phone if that application doesn't have permission to access your camera, but it still has access to a certain amount of things that it is allowed to access, and that's what we're talking about today. So one kind of system is having a rule-based sandbox where we basically launch an application into a sandbox. So, and then that sandbox can enforce exactly which files that program's allowed to actually access. And the example that we talked about last week is system call interposition, where we have basically a filter on the system calls that the application's allowed to make. So if the application says to the operating system, hey, I want to open this file, we can filter out the system calls and say, open the file. No, we're not going to let that through to the kernel, for example, and we'll just filter that out. So it's defining rules based on system calls. So does anyone here want to remind us what a system call is? There's not many of you here, so if no one has an answer, I will forgive you.
It's essentially a command to the kernel to...
Correct. Yeah, so it is communication or a command to the kernel to do something. So for example, open a file, and the kernel basically does the actual hardware interaction and things like that. So yes, so a program makes a request to the kernel, and at that point we can use that to basically make security decisions. There are some disadvantages to system call interposition, is that system calls can be incredibly complicated, and you can have interactions of system calls which end up in this quite complicated state. So for example, just to open a port to listen, open a network connection involves a number of system calls to actually bind to a port and start accepting connections and things. And if those happen in different orders, that can change what actually it's doing. And so it can get quite complicated to do system call interposition. And it's not really an ideal solution. It's much better if you design it into the operating system itself. So if you remember when we were talking about design, secure design principles, one of them is principle of complete mediation. And if you have different rules being applied in different places, it can be harder to make sure that everything actually is being enforced. Whereas if it's in the kernel, there's less likelihood that someone's going to figure out a way to subvert that security mechanism. So the next thing to talk about is rule-based system-wide controls, where instead of basically saying, okay, I want to start this program in a sandbox, you just treat all applications as if they have rules that say what they're allowed to do. So you have all the different programs that are running on your computer, and they all have different sets of rules that say what each program's allowed to do. So it's really similar to what we were just talking about, except that now it's just the operating system just has a number of rules for each different application or a different process.
Would that be that every time a user installs a program, would have to set up rules for every program, essentially?
Possibly, but it just depends. There's all these different kinds of systems, like security mechanisms that do this in different ways. Some might do that where once you've installed an application, you just have to set up the rule for that application. There might be a default set of rules for any application that doesn't have a rule that you've specified. So yeah, there's lots of different ways that they can handle that specific situation. Usually these security controls are mandatory, which means the user doesn't get any choice, and it's the administrator of the system. And if it's a one-user system, like most are nowadays, and you have your own computer, then you as the administrator of your own computer can specify the rules for your applications. But if there are multiple users using a system, often whoever's the administrator gets to choose what the rules are for each application. So because each application that's running has this, quite complicated policy that says what it's allowed to do, you have to think about what happens when one program starts another program. So for example, if Firefox is allowed to delete its own files, what happens when Firefox actually starts the rm command to remove a file, for example, if it did that? There needs to be you need to think about what happens in that situation, because the rm command needs to be able to delete any file on your computer, probably, because you're going to use it to delete all sorts of files. But you don't want Firefox to be able to delete every file on your computer. So you might say, well, in that situation, you just have the Firefox policy specify what RM's allowed to do when Firefox starts it. But when another application starts it, maybe something else happens. What happens when Bash starts, so it's quite complicated. But that's known as a policy transition, where when one application starts another, so what happens when Firefox starts LibreOffice? What policy is going to apply? So that's known as a policy transition. When one application starts another, the rules might change for that new application. So broadly speaking, there's two kinds of security system that do rule-based system-wide controls, and there's coarse-grained rights and fine-grained rights. So coarse-grained is like on Android, for example, where you have some really high-level permissions that the application is or isn't allowed to do. So for example, access the camera, access your SD card, everything on your SD card, access your the ability to send SMS messages. So, there's like these permissions that you can give that application, and it allows it to do those high-level things. And we'll come back to Android security. And there's also a system called Bitfrost, which is basically a very similar kind of thing, where you have applications and you give them access to high-level things. Linux capabilities do that for the root permissions. So if we remember, root is the super user on a Unix system or a Linux system. If it's got a UID of 0, then it's root. And what Linux capabilities can do is break up that superpoweredness of root, so that you can actually have someone running as root, a program running as root, but without the ability to do certain things that root can normally do. So you can actually drop some of those special powers that root has. So for example, you can allow an application to access raw network without granting everything else that root can do. So if you remember when we covered, and I think you asked me a question in the lecture about this when we were talking about sudo, setuid, talking about the ping command, which is setuid 0, so that it could access the network. And if I can remember correctly, your question was something along the lines of, yeah, but that means the program can do everything else root can do. And yes, except we've got capabilities which allows us to actually say, yeah, but ping doesn't get everything else that root normally gets. It can be UID 0, but it can't do all the other root type things. So Linux capabilities kind of neuters, or kind of like takes away some of the sting of the fact that root is just this ridiculously powerful user on a Unix system.
Just to build on the ping question,
yeah.
Is there a way so that you wouldn't have to put the that you wouldn't have to run sudo to run ping.
No, yeah, you don't have to run sudo because setuid is set for the file. So if you remember, setuid allows you to specify the file permissions for a file and say when this program is executed, it runs with the effective UID of whoever owns that file, that program file. So in the case of ping is set to be owned by root and it's set UID, so whenever anyone starts ping, that program is running as root, even though you started ping. And the obvious risk involved in that is if there were any programming mistakes in ping, because you're starting it and you can feed information into it, you could break the ping program and become root on the computer when you're not supposed to be root, you're supposed to be a normal user. So there is a big risk whenever you use setuid. But Linux capabilities take away some of that risk, because now if you manage to break ping, you can't necessarily do everything that root could do. You might be a root user, but actually you can't, for example, start accessing, opening, I don't know, all the other things that root can do. You can't necessarily just start deleting files or yeah. So it depends on which capabilities it's been given. So I think there's a capability called DAC override or something, which basically means that root gets to ignore all the file permission checks. You can just do anything it likes. If it doesn't have that capability, then if it tries to delete a file, for example, that root is not specifically told it's allowed to delete, then it wouldn't be able to delete it.
Yes, that's what's Bitfrost? Is that the build by OS?
Bitfrost, from memory, and I haven't looked at this for a few years now, I think is a very similar system that was designed for the One Laptop Per Child project, which was basically they were trying to create a cheap like netbook for third world countries and things so that they could do educational learning and stuff on it. And Bitfrost was the security mechanism built into that system. And I haven't looked at that for a few years, so I might be wrong, but if I recall correctly, that's what it was.
Yeah, that's really because I haven't heard of it before.
Yeah. So Linux capabilities. So normally we've either got privileged users, UID 0, or everyone else, which is not 0. Root can do everything. But capabilities divide those privileges up. So another example that I didn't mention is cat chroot. So without that permission, you can't use chroot to change the namespace of a program, which is a type of sandboxing that we talked about for last week. So you can actually grant or remove a capability from an individual process. So you can actually, the program can be programmed to drop a capability. So a program that's running can say, I no longer need the ability to use these things. So it will just drop, say, I don't need the ability to do chroot. So drop that permission. I don't need the ability to access the raw network, so drop that permission. Can you think of any example? Why would a programmer want to drop permission from a program?
I was just going to ask, surely it should be the other way around, because if a program can choose what to drop, why does it have to drop anything?
Can anyone think of an answer? Why as a programmer you'd want to drop permission?
I presume the answer was, well, if the code was to break.
Yeah, exactly. So you're planning for worst case, where maybe I've made some programming mistake somewhere in my code, and if I'm running as root, for example, I don't want someone to be able to take control of this program and do all sorts of horrible things. So I'll say this program, well, I don't need all those other permissions, so just drop them. So for example, ping, instead of using, one way you could do it was for ping to actually say explicitly, look, and I do want to keep the ability to read and write from the network with raw network access, but all those other capabilities, I just want to drop them. I don't want them. And you can actually remove capabilities from an entire system. So there are capability bounding sets, so you can actually say, for example, this whole computer, I never want any program that's running on this computer to ever load a kernel module. So a kernel module is like loadable kernel module on a Linux system is like a driver, for example, and it loads the code into the kernel itself. From a security perspective, it makes a lot of sense to not allow people to do that, because otherwise, if anyone ever becomes root, they can load a kernel module and get even more access to the computer, because the kernel is like this all-powerful thing on a computer that can literally access, well, is the thing that arbitrates all access to everything. So if you can load into the kernel, you can install like a rootkit or something, for example. You could have a kernel module that doesn't show certain programs the correct list of processes that are running on a system, or can hide things from programs. So we might want to just remove that from a system. Domain and type enforcement is a specific kind of access control, which allows you to say this program is of type whatever. So you might say the type might be Apache or web server. And we actually label every file on the computer with a type that says, what type that file is called. So we might say every user in the home directory, every file in a user's home directory is of type home directory. And then if we wanted a specific program to be able to access any of the files that are labeled that way, we specify a rule that says that. So just then when I was talking, I called the program, I said you can label a program with a type. That is true according to the terminology that some people use, but there are other domain and type enforcement that would say that that is actually a domain, hence the name domain and type enforcement. So you say, this program has a domain of this, these files are all labeled with types, and then you have a set of rules that say which domains can interact with which types in which way.
I was going to say, what's the definition of domain here? Because there's quite a few like networking files, there's domains. And
you just forget everything that you've ever heard the word domain used for before, and it's like a separate thing. so it's just, it's like, you could think of it as the name of the sandbox or the name of the security profile. So you can say this program starts off with domain Apache. So when the program Apache starts, it has the domain Apache, and then you have a file that has a policy in it that describes the fact that Apache domain is allowed to access files that are labeled www, for example. And you probably wouldn't give it permission to access files that are labeled home directory. So that's how domain and type enforcement works.
I presume you can, with that example, you could select multiple programs to have Apache as the domain.
Yes. So you could, you can have, instead of calling it the domain Apache, you might call the domain web server, and you might have Apache and some other web server running on the same computer and give them the same domain, and then they can all access the same web files. Probably, I'm not sure if that would ever make sense, but you could do that. Yeah. SE Linux, I guess I'm just curious, show of hands if you've heard of SE Linux, you've heard the word before.
Heard of it.
Yeah, show of hands. All right, yeah, actually quite a few of you. So probably you don't know what it is though. So it's like this incredibly complex security mechanism that is nowadays included in Linux, the Linux kernel. It's often disabled, it's often not used, but it depends what distribution of the Linux you're using. So if you use Red Hat or Fedora, it will be turned on by default, and if you use Ubuntu or Mint or OpenSUSE, it'll be turned off by default, because there are security mechanisms called LSMs, Linux security modules. You can only ever have, as of, this might change in the future, but you can only have one enabled at once. So you kind of have to choose between these security features, and some distributions choose SE Linux. So it was created by the NSA, and there was speculation at the time. It's like, oh, there's some backdoors included in there somewhere, but Actually, there's no evidence that that's true. It's all open source. It's been audited by loads of people. Actually, it's probably the most comprehensive mandatory access control system that exists in common use in the world, I would actually say. Like, it is incredibly complicated and incredibly powerful piece of restrictive software where you can actually set these incredibly complicated rules, and it's perfect for something like if you were in the military and you wanted to be able to specify mandatory access control rules based on having top secret people that can access certain kinds of documents, and you never want people that have lower security clearance to be able to access those files. Like, SE Linux is perfect for that sort of stuff. Like, it's really, really powerful. But it's also incredibly complicated. Like, it's ridiculously complicated. So it has domain and type enforcement, I was just talking about, has role-based access controls, which we've talked about previously. It has all these different security models built into it, and they all kind of relate to each other. So you've got like, you kind of have to think about all of them when you're designing a security policy. And every file on a Linux system that uses SE Linux needs to be labeled with a security label that defines the type. And on SE Linux, they refer to programs as having a type associated with it as well, which is why I mentioned that instead of domain. But you can also call it a domain if you like. So you have the rules are incredibly complicated. You have these different types or domains for all the different programs that are in the system. You have all these very complicated rules about what they're allowed to do to the different files. You've got thinking about like role-based access controls and all that, and multi-level security and all these different things. But it can do some really, really powerful things. The saying is that the most commonly asked question about SE Linux is, how do I disable it? Because on an SE Linux system, if you actually confine Apache, for example, and you do it correctly, and you try and copy a file from some other place, so for example, you copy a file from your home directory into the Apache directory, if you don't relabel the file system, Apache still won't be able to access that file because it's labeled with the wrong security label. So it's just like, it's quite complicated to manage, so then you have to run a command that relabels the files in that directory, and then Apache will work again. It's incredibly good. You could really lock down a system with SE Linux, but actually it's not designed for human beings. It's not designed for regular folk to use, to be honest. Like, it's really, its best use is when it's configured by the SE Linux guys to lock down core features of Linux. So if it's configured correctly, then hopefully you'll never ever know that it's even running. Like, if you're not confining things like Apache and it's just like core aspects of the operating system that is being confined, possibly you'll never even know that SE Linux is on that system. But if there was a vulnerability in that software that's being confined, it will stop that from becoming a huge security problem. So their argument is, well, yeah, it's hard to use, but you shouldn't be using it. Just if we've set it up properly, just believe us that it's like making you safer.
So that make Red Hat and things more secure because that's enabled by default and presumably set up correctly.
That is the argument, yes. So if you are using Red Hat and you're using SE Linux as it's being configured by them, then the argument is that you've improved your security and you'll never even care that SE Linux is there. If you wanted to use it to do extra things, then you can spend a week reading about SE Linux and learning how to use it properly. There is an SE Linux aspect to the lab exercises that you can have just a brief look at using SE Linux. So an alternative approach is what AppArmor and Tomoyo use, and they've kind of designed a much simpler type of system that does something in a similar way. So you could use SE Linux if you're working in the military and you really want to lock down a system. If you have your own server that you're trying to manage yourself, you might choose to use AppArmor instead, because the rules are much simpler to understand, because they're based on human readable paths instead of having labeled file system. So for example, you could say, this program, Apache, is allowed to read everything in var/www, whatever. And this program can access everything in this directory. And you have like a list of directories or files that a program can access. And the rules can still be quite complicated. There might still be 100 rules because programs do access lots of different files on a system. But you can actually read the rules and make sense of it. There are learning modes available where you can basically say, okay, I trust that it's going to do the right thing this time. So you start your learning mode, you start up the program, and then it records everything it wants to do. And then it says, are you happy with these rules? And you say yes or no, or you can change each individual rule. But that way, if there was a security vulnerability in that code, then if it tried to access anything that it didn't access the time you generated the set of rules, it wouldn't be allowed to do it. So it would restrict any damage that could happen after you've set the rules. But if you are running some malware, obviously that's only going to work if you correctly read vet the actual rules that are happening. If you try and run some program and actually it's trying to do all sorts of malicious things, and you're looking through all of these rules of all these hundreds of files the program's trying to access, more likely than not, you're probably going to miss the fact that that program's doing something malicious, in which case AppArmor hasn't helped you at all. But it's something that a mere mortal that's like their catchphrase is like something like mandatory access controls for mere mortals. So as a human being, you can actually configure AppArmor and create something that was probably more secure than if you didn't have AppArmor.
I was going to say with AppArmor with the learning mode, if you ran malware through that with that on, surely then it'd be too late because you'd already run the malware.
Yeah. Well, you can. I believe no. I don't, yeah. I mean, you're right because you can't. Some security controls you will actually interactively decide, like it pauses the program while you make the decision. But with AppArmor, I don't think there currently is that feature. So yeah, you're right. It's allowing it to access that stuff. But still, if you did audit the rules and you saw it was doing something malicious, at least you'd know it was doing something malicious, and potentially you could say no, never do that again, and limit the damage that could happen. But yeah, it's not really ideal for malware for a few reasons. Can you think of any advantages or disadvantages that I haven't mentioned for that approach to security? I think we pretty much covered the pros and cons. It's like, yeah, it's easier to use, but it's slightly less secure. In terms of like moving files around, what that means is by moving a file, you're changing which programs can access the file, which the AppArmor guys say, well, actually, that's exactly what you want in real life. When you move a file from your home directory to the Apache directory, you're kind of saying you want it to be able to access it. But the SE Linux guys will say, well, no, because unless you've specifically specified the security rule that says that it's allowed to access that file, that could actually be a security breach. So arguments on the other side. So just as a side note, I'll mention that my research that I did for my PhD was related to this problem and actually coming up with a much friendlier, user-friendly approach than what AppArmor does, but by restricting programs based on the features that you want them to be able to perform. So you can say this program is a web browser, and then it can access certain files and things. But that just a side note of what my research that I've conducted was. Integrity levels. So on Windows, everything newer than Windows Vista, you have integrity levels in Windows, which basically Windows system is similar to Linux in that most of the security decisions are based on granting privileges to users or groups, which are represented by SIDs, security identifiers. But starting from Windows Vista, there's a new access control entry, or ACE, which a type which represents an integrity level. And what that allows you to do is restrict programs that are less trustworthy. And there's a link there if you want to find out more. But basically, what that means is you have some programs that run at a lower integrity level, and sorry, and they can't access any files from any of the programs that are higher integrity level. So the example is that Internet Explorer by default runs at a lower integrity, so that you can't actually access other things on your system without interacting with the user. But in Windows Vista, there's no actual graphical tools to configure it. It's just one of those things like SE Linux that they don't want you to try and use this yourself, but Microsoft will set it up for you so that certain programs are restricted. So that means if, for example, you install Firefox, it doesn't have that extra layer of protection. It doesn't use integrity levels. It's only for Internet Explorer. That may have changed in newer versions of Windows. I'm not sure.
So just having Internet Explorer on your system would make the system worse anyway.
I would certainly argue that point, yeah. So other integrity-based schemes are like the seminal Beaver access control model, which was the one of the first access control models around integrity, and I'm pretty sure we discussed that a few weeks ago when we were talking about access controls. So an integrity-based scheme is essentially a mandatory access control, and it might improve security, but it doesn't actually confine an application to only what it needs to be able to do. So it's not really a sandbox, but it does provide some protection against it doing something malicious. But then again, if you have a whole bunch of files, a whole bunch of programs that you don't trust, and you put them at a lower integrity level, well, they can all interact with each other and mess with each other's files, just not with everything else that's on the system. So starting in Windows 8, we have app containers. So if you've got a Metro app or a modern application, the really ugly ones, they're Sandbox using an app container. So every individual app is restricted to its own app data directory, and any other access to documents or media or anything requires specific permission or user interaction. And it's basically each of those applications is a new integrity level. So each of those programs running gets its own integrity level, and each application gets its own SID, as opposed to just having users or groups that have SIDs. So kind of like in Android, you have applications that declare which capabilities they use ahead of time. So before the program even starts, there's like a list of like a manifest file, just like in Android, we have this program, the author say, I want it to be able to do these things. So for example, I want it to be able to access the internet, and that might be a capability that it specifies. And then once it's installed, it's allowed to access the internet, but it's not necessarily allowed to access other things. So there's a few links there if you wanted to know more about that as well. So Android is mostly free open source operating system. I say mostly because it doesn't use the GPL license, so it's not copyleft software, which means that companies like Samsung can basically change Android without making their changes public. And obviously the commercial argument for that is one where there are companies that might be more likely to use Android if they're free to make whatever changes they like. So it depends what your position is on open source software and everything. But so if you're using Samsung, you've got a lot of not open source software as well on your phone, but the core Android itself is open source software. So Android's obviously very popular. Show of hands, Android. All right, a couple of you are wrong. No, yeah. So yeah, it's based on the Linux kernel. So the actual kernel itself is a Linux kernel. It used to, at one stage, be a fork of the Linux kernel in that, I won't get into it. There was a very big argument in the Linux community because, briefly, Google took the Android, the kernel, the Linux kernel source code, and then without communicating with any of the Linux folk, just made all their changes that they think they needed to make for Android, and then released Android before they even talked to the Linux community about the changes they'd made, and then tried to push all their changes on the Linux community. Like, well, no, actually, you should be doing it a different way, and it was a big argument about it. It's all resolved now. It's all resolved, and now it is basically it is the Linux kernel. But everything else on the system is nothing like a Linux system that you know of. So the GNU Linux distro is made up of, the Linux kernel and all the GNU software and all the other software that's been developed by the free and open source software community. Whereas this is just the kernel with basically this Java stuff on top of that. So Google went away, re-implemented the entire Java system. So they used the same API. Well, they were based on Apache Harmony, I think it's called, which is Java not programmed by Oracle, basically. So it uses all the same APIs. So if you know how to program Java, you can program for Android, but doesn't use any of the source code for the original Java and the actual Java virtual machine. So the thing that interprets the bytecode to run the program is different. So it's the Dalvik is the virtual machine, and I believe they've got a new one now, which is an alternative that they're looking at changing to. Does anyone know the name of it? Can't think off the top of my head. They're actually starts with an A. They've got another alternative virtual machine as well that they're thinking of changing to. So the architecture looks a bit like this. You've got all the applications at this top layer, and these are generally programmed in Java. And you've got the actual application framework. You've got all the libraries and things, and some of this stuff is written in C. And you've got the actual Android runtime, where you've got the actual Dalvik virtual machine that runs all the apps that are written in Java. And then on the bottom layer, you've got the Linux kernel talking to the hardware. So all this stuff is, this is all written in C. Some of this is written in C, and this is written in Java, basically. So the way that I said all of this is written in Java, but you can have native code in an application as well. So you can have C code included in an Android app. But the way that it's confined is that the applications specify, like in Windows 8, although Android came first, in a manifest file, it says what it needs to be able to have access to. So for example, the manifest file might include this line, which says that it wants to be able to receive SMSs. And once that application is installed, it can receive SMSs. There's a whole bunch of different permissions that you can see that give you access to different kinds of things. So an application can request any of these permissions, and it will give it access to different kinds of things. An application can also define its own permissions, and it can do things like communicate to other applications that are installed and provide services that other applications can access. But you need to be careful when you're programming that kind of thing. But the Linux kernel actually enforces the rules of what each application is allowed to do, and because it's all running on the Linux kernel, this is going to make a lot of sense to you. Basically, because Android was originally developed to be a single user system, so we never expected two people to share the same phone, they actually overloaded the UID mechanism that's on Linux to basically be that each application installed gets its own UID. So every application that you install on Android gets a new user ID so that it specifies what it's allowed to do. And you also get specified groups, which basically represent the capabilities or the permissions that it's requested in the manifest file. So you've got groups specified for each application as well. And there's a config file that basically assigns permission names to group IDs. And so you only have one user, but you have all your applications combined separately. Side note, recently, about a year ago, there's a version of Android where you can have multiple users on like a tablet device, not a phone, but on a tablet. The way they did that is using Etrace because they'd already used the Linux UID mechanism for confining separate applications. So in order to have multiple users on an Android device, they use Etrace to basically separate these different instances of Android from each other. It's like it's kind of almost bizarre the way that they've done it, but I mean it works. So on an Android device, you sign your code. So you use a digital signature to say that I created this code, but it's self-signed, so it doesn't prove anything about whether you can trust the person, because you can generate your own certificate, sign the application, but it does allow you to make sure that you can have applications that share the same UID. So for example, if I as a developer create a file reader and a file writer, they can all access each other's files because they get the UID of the author kind of thing. It's based on the certificate used to sign it. So no one else can, unless they've got my private key, create another application that shares the same UID. So UIDs actually get signed when you install an application, and there are some built-in applications that have their UIDs hard-coded. So applications are installed by users, and obviously there are app stores from Google or Amazon where you can, they've basically done some vetting for you, some. So Google do some static analysis and can remove applications from devices remotely. Users can choose to install apps from anywhere though. So there's, you can go into the Android settings and just say, allow me to install applications that don't come from a trusted source, and then you can just download something off the internet and install it if you like. So there's a system called Bouncer which does that, which runs a program and checks, does some checks to see if it's malicious before accepting it onto Google Play Store. And when you go to install an application, Google Play, for example, will list the permissions that it's asking for. And nowadays, they've simplified the interface possibly too much. This is what it looks like when they list everything that the program's trying to do. And then, as a user, you have to decide whether or not you're going to install that application and therefore allow that application to do all the things that it wants to be able to do. So I guess the question is, do users actually read and understand this security prompt? Anyone think yes? I'd say probably most don't. So that's definitely a security usability problem, which coincidentally is one of the security questions that we have on our research group that we're looking at for Android security. But yeah, it's definitely a complicated problem, and it's not an ideal solution. So on Android, there are Trojan horses that have made it into the app stores. You've got SMS Trojans that actually send premium texts. Others collect information from the user, basically spyware. And there's been all sorts of things. And because we're running out of time, I'll just say that malware can be a serious problem on a phone. Think about it. You carry this device around in your pocket. It's got a microphone attached to it. It's got a webcam. It's got a camera. It's got a GPS. It's got everything you'd ever want if you were trying to spy on someone, for example. So if you manage to basically hack into someone's mobile phone, then there are all sorts of things.
There's also money with Bitcoin and things like that.
Well, yeah, money. If you've got, you might have your banking applications on there, and Bitcoin and all sorts. So yeah, it can be quite serious. And if you ever watch the TV show, what's it called? What's the I think the show I'm thinking of is the guy with the glasses, and he talks, and there's the guy that follows people around and just clicks a button, and he's hacked into someone's phone and starts listening to the conversation. Anyway, it doesn't matter. I don't watch it that often, but so yeah, there's all sorts of security extensions for Android. There's SE Android, which is basically SE Linux, is now included in Android, and it basically locks down some of the core operating system parts of Android. It's not used to confine most applications; they're just some parts of the system. And there's all sorts of things that you can do to improve the security. iOS is a bit different, which is Apple's thing, and I won't shame anyone by asking for a show of hands. But there still is a sandbox on Apple devices. So every application runs in a sandbox, and it grants more or less the same permissions to every application. So every application on an iOS can access your contact list, for example. But they do have separate directories that each program has its own kind of sandbox where it has its own information. Every application can also access browsing history, but there are some interactions that the user has to actually approve. So for example, if an application wants to access your GPS location, I think it'll pop up and you have to like approve it. But their general approach to security is a walled garden approach. So they basically say you can't install any application that Apple don't approve. So it's impossible for you to install your own software on your own phone without Apple's permission, basically, unless you pay them $100 to be a developer or whatever. They also obviously get a cut of any of the sales from any of the apps that get sold. It used to be the reviews process to actually get an application included in the App Store was very obtuse. Like you didn't know why they made the decision, but it's a bit clearer nowadays. Some users jailbreak their devices, which basically allow them to install their own software on it. It allows them to root the device, so they get admin control on their own device. And there has been malware that targets rooted iOS devices. So there was a worm that locked the screen of iPhones and requested a ransom, €5 to unlock it. So there, applications in the App Store often they collect personal information from the user's device. Possibly there's less malware for iOS than Android. Quite probably there's less malware, and that might include some of the deterrents is, because you have to pay to develop for iOS and you actually need a Mac desktop system and you also need to provide some user identification when you sign up. I think that does put some malware authors and things off creating malware for iOS. So there is less malware for iOS than Android. So some of the things to think about is just like, do you own your own device or are you kind of leasing it? And how important is the freedom on your own device? And what if we applied all those same ideas to a PC? Would you use a computer that you couldn't install any software on that someone didn't approve? Just something to think about. Web app security, but I'm not going to talk about that. So in conclusion, you now know a variety of ways you can use to protect yourself from applications. So when there's malicious code running on your computer, these are things you can do to basically restrict the kinds of damage that can happen. This is very much an active area of research. In some ways, there's a lot more that needs to be done because a lot of these systems are just either incredibly difficult to use or there's just big usability problems in them. And there's a lot of area for improvements to be made. So that's all for this week, and I'll see you next week. Thanks, guys.